So as I mentioned, today is a review. We're going to go over a couple of concepts that I covered at length in the Intro Spatial Data Science course in the fall. So for those of you who were there, this will be a refresher. I will not do the review of matrix algebra, don't worry. I gave you the chapter in green, which is an excellent review. So if you just want to skim that to make sure that you have the basic concepts straight. I will be using matrix notation pretty much throughout. So if you're a little rusty on that, make sure you get more comfortable. Then I'll do some definitions. I do want to start head on and deal with some of the pitfalls of this type of analysis, the kinds of things you're confronted with when you do make presentations in a non-friendly environment, let me put it that way. And then we go over the concept of spatial autocorrelation, which is so central to a lot of the things that we will do, and spatial weights. Again, this is a concept and also a tool that we need for all of this analysis. And then Monday we'll do kind of a lab practicum where I'll walk you through how you use and construct spatial weights in both GeoDa and GeoDa space, and also a little bit in R for those of you who might want to use R for your analysis. In terms of readings, so I mentioned last time that there is a reader. The reader is not quite complete, so there are some additional things that I add to the Canvas site that supplement the reader. I also, in the first part of the Canvas site, you have a PDF of the Modern Spatial Econometrics book, PDFs of the 1988 Spatial Econometrics book, and then the big review chapter. So the readings are basically the one is an introduction, an overview of spatial analysis. If you really have no clue what this is, I would recommend you take a quick look. It deals with exploratory data analysis, spatial regression, and spatial optimization. I can't touch on spatial optimization here, but that's a whole course in its own right. And then the relevant sections in the Anselin and Ray book, the green matrix review, and then a little more technical article that deals with how to efficiently construct higher order weights if you're interested in some of the technicalities of these things. And then the lab is really 4 Jupyter notebooks that I have on the Canvas side that basically walk you through some basic matrix operations using NumPy. So if you're rusty with NumPy or you want to find out how NumPy works, it's all Python. You know, you just go through the notebooks and you just do shift enter, shift enter, shift enter, and it works you through the whole, all the steps. So that's there as a PDF, so you can just read it to see what it does, or you can actually download the workbooks, the notebooks, and step through the code. Okay, so let's start with just 1 minute. These are the kinds of concepts that I want you to be comfortable with. So quadratic forms, you know, what a matrix is, how you multiply them, matrix multiplication, vector matrix, matrix vector, all that stuff. Concept of a matrix inverse, not so much how you compute it, although you can get into that as well, but just know what it is and how you, where it comes into play is solving systems of linear equations. Determinant is a concept that we will see in the specific context of the Jacobian of a transformation. So if you know, a little rusty on your calculus, when you transform a variable to a function of a variable in order to make sure that this new variable has a proper distribution. So probability distribution means it sums to 1, nothing is negative, nothing is larger than 1. Then you have to rescale that. And the rescaler is called a Jacobian, and that's a determinant. And we'll use that for spatial processes. Cholesky decomposition is a way to compute the determinant efficiently. Eigenvalues and eigenvectors, we'll talk about them. We will try to avoid using them because they don't scale up well. And then if you're really a geek, like me, matrix partial derivatives. Cool stuff, right? I will mention them, but we won't go over them. So first, some definitions, right? What is spatial analysis? And I do this, and some of you may have seen this multiple times because it's in all my slides and all my presentations. So what actually makes an analysis spatial? And the distinction is not always obvious, but it has to do with situations where you combine attributes, value, measures, with the location. And the location matters. So in standard non-spatial analysis, non-spatial statistical analysis, regression, whatever, the location doesn't matter. In other words, you can take the same data points and put them in different positions on the map and you get the same results. Spatial analysis, that's not the case. Spatial analysis, location, distance, relative position, all these things matter. And if you change those, the results change. You know? So the concept where you don't need spatial analysis is called locational invariance. So it doesn't matter. But when it does matter, you will need spatial analysis. And let me just give you an example that, again, many of you might have seen before. These are two Milwaukees. One is the real Milwaukee, the other one is a fake Milwaukee. These are census tracts in Milwaukee with the percentage African American. The one on the right is fake. The one on the left, let's see. The one on your right is correct. The one on your left is fake. So Milwaukee, just like Chicago, is a highly stratified, racially stratified, or you could say segregated city. So that's what you see here in the picture on the right. It's very clearly structured, right? Then the picture on the left, we take these same values and we shuffle them around randomly, right? So what is tract A in the first picture becomes tract B in the second one. And so this is an example of a non-spatial analysis. So we do a histogram of the percent African American by census tract. For the two maps, these histograms are identical. You cannot tell the difference because the numbers, the values are the same. Where the values are is not the same. So with this kind of analysis, you don't capture that. But with this kind of analysis, which is called a Moran scatter plot, it is a way to visualize and measure spatial autocorrelation, which we'll talk about in a few minutes. Here you can see the difference. In the random map, it's flat. There is no spatial autocorrelation because by construction, it's spatially random. It should be like that. The other one is the real one, and it has very high positive spatial autocorrelation, which indicates clustering of similar values. So in other words, a high degree of racial stratification in the city, right? So that's the difference between the two. And of course, what we will be concerned with is dealing with situations in regression analysis where there is a difference between the two. So we won't focus too much on specification tests and methods where location doesn't matter, but we will focus on the ones where there is a difference, whether or not you take this into account. So spatial econometrics then, at least the way I think about it, is a subset of econometric methods. I mean, I use this term because that's where I come from. I was trained as an econometrician, but now I call it spatial regression analysis because it really, as these fields evolve, I mean, there's some tension between sticking with the theory and then you would call it econometrics, or going to the data and then you would call it more regression analysis or predictive analytics or whatever the current term in vogue is. But originally this came out of regional economics or regional science. So it was a concern of how do you put these spatial theories into regression form and how can you estimate them. The differentiating characteristic is that you have an explicit treatment of location, where the observations are, distance and arrangement. So location is absolute location, Distance and arrangement you can think of as relative location, positioning, and you bring that into 4 major aspects of the modeling exercise. The specification of the model, estimation of the model, specification testing, testing whether your model reflects the data properly, and then prediction. Prediction we won't deal with in this course. I mean, even though there's all this hubbub about predictive analytics, and you'll see why as I go through the course, it's less of a focus here. Here the focus is on inference, on statistical inference. So what happens to your regression estimates when you ignore spatial dependence, when you ignore spatial heterogeneity? How can you detect that? And then how can you fix it? How can you change the specification to incorporate spatial dependence, incorporate spatial heterogeneity, and how does that change the estimation methods that you can use? That's really what it is about. And so the 2 main effects are dependence and heterogeneity, and these of course are the classic works that treat this. Both of these, I'm just kidding, but both of these are available as a PDF. But the 2 spatial effects, there's a big difference between them. So spatial heterogeneity is basically there's nothing to it. If you know your econometrics, you can deal with structural change, structural breaks, varying coefficients, and all that stuff. The only differentiating characteristic is that the structure that you put into place has a spatial interpretation. So it would be core versus periphery, urban, rural, north, south, east, west, something that has a spatial regional interpretation, right? So they become regional effects. You test for regional homogeneity. Does a particular function, say something that explains crime, is it the same in cities as in rural areas? If you do house price functions, I'll talk a lot about hedonic price functions. Are they the same in different regional submarkets of the city, right? So is what you get for an extra garage, is that the same in one neighborhood versus another neighborhood? And how do you model that? How do you check for that? So that's all standard econometrics, but it becomes spatial because the structure is spatial, right? Spatial dependence is a totally different story. So as I already mentioned the other day, it is not time series in 2 dimensions. It is two-dimensional, but it's also multi-directional. And the key concept there, and I'll mention this several times, is I am my neighbor's neighbor. So if I influence my neighbor and my neighbor influences me, then in some sense I'm influencing myself. And so if you think of society or economic agents or other agents as interacting in some kind of network structure, then all these interactions kind of bounce back in the system and they create a simultaneity, and that simultaneity has to somehow be corrected for. That's the crux of the estimation problem dealing with spatial dependence. So this is very different from time series where you have a clean direction from past to future. The future doesn't influence the past. In space, in some sense, it does, because things bounce back, especially in a cross-sectional sense. So then, if you have panel data, if you have both cross-section and time series, you have the combination of both. And then you have potentially, interaction effects that are contemporaneous at the same time, or they're in space-time. So what happens to your neighbor in a previous time period affects what you do now. And so all these things are the kinds of phenomena that we'll be looking at. So as I said, 4 basic dimensions, specifying the structure. So we'll cover that about 3 lectures from now. We spend a whole lecture on specifying spatial dependence and then a whole lecture on specifying spatial heterogeneity. Testing, specification testing, which in practice is probably the most relevant thing you will do, in my experience, and this is, you know, a casual empiricism, but in about half or a little more than half of the cases, there is no problem of spatial autocorrelation. So if you have your problem model specified properly, you're working at the correct scale of observation, everything falls into place very nicely, you don't have to worry about it, right? But by the same token, in about half the cases, you do have to worry about it. And so the specification tests will tell you whether you have to worry about it and how serious it might be. Now, in some cases, you know, how serious this is all a bit relative. You know, I'll be the first one to say that sometimes in practice, at the end of the day, it really doesn't make that big a difference in a qualitative sense. You know, if you have, say, a coefficient in a regression that is significant at 0.00000001, whether or not you correct for spatial correlation in the error terms, maybe we'll chop off 1 0, but it's still going to be highly significant. And especially in this day and age of larger data sets, that's kind of a subtlety. It matters when you do prediction, because the prediction precision is affected by the precision of your estimates. But if you're just interested in finding out what is significant and what is not, probably is not going to make that big a difference. Now, in some other models where you in effect misspecify or don't specify at all the structure of spatial interaction, then things can be very wrong. And in linear models, this is still, you know, relatively speaking, probably not a disaster, but it will give you, could give you wrong signs. So if you do a policy experiment and there is strong interaction and you ignore it, you could get a positive sign, whereas in fact it should be a negative sign, or it really is a negative sign. But it really bites you in nonlinear models. Because in nonlinear models, things are much more sensitive to the assumptions that you make. And if you have strong dependence in nonlinear models, pretty much, you know, everything falls apart. So we'll be testing. We'll look at, as I mentioned the other day, specifically maximum likelihood estimation and generalized methods of moments, or methods of moments, as the two main paradigms to estimate the models. I mentioned there's a third main paradigm, which is the Bayesian paradigm, which would take a whole course in its own right, and maybe one of these days I'll do that, but not this year. And then spatial prediction we'll just mention when it happens to be relevant, but that will not be a major focus of this class. Okay, so before we get all excited about these methods, let's step back a second and think about what can go wrong, right? And the biggest one, the biggest criticism of this kind of analysis, which is typically but not necessarily done at the areal, in an areal unit of aggregation. So a county, census tracts, you know, police wards, those kind of units, is that the typical mistake that is made is that the model is estimated at an aggregate level. So for example, you have proportions of people with a particular disease, and then you interpret the results at the end of the day by making inference about individuals. That's a no-no. That's what is called an ecological fallacy. And it has a lot to do with micro-macro aggregation. It's basically an aggregation problem. So if you aggregate up from the individual level to a spatial scale, to what extent can the relationships that you identify and estimate at that scale be turned back down to individuals? Or basically they cannot. Right? But that doesn't mean you can't do spatial models at the individual level. You can. As long as you have an interaction structure, you can also do these models at the individual level. But the typical application is at a spatially aggregate level. So we have county data. You look at county homicide rates, and if you're not careful in your conclusion, you say something about criminals or criminal behavior. Well, you can't. You can say in counties with, say, larger unemployment rates and lower average family income, there tends to be a higher homicide rate. That's perfectly legit, and for policy purposes, that the county may be the unit of allocation of resources, right? So then you allocate your resources to these counties where they're needed. But that doesn't tell you anything about individual criminal behavior. And similarly, say if you look at disease rates, you're modeling the rate in the county or in a census tract, but not whether a particular individual will get sick or not. You know, that is a very different thing. So as long as you keep that in mind, you'll be fine. It's very easy to fall into the trap and to make that jump. So as long as you think of it as an aggregate model, aggregate interpretation, you're fine. And of course, the alternative is when you mix different levels is multi-level modeling. I'll talk a little bit about that, but there's plenty of courses that deal with that, so I will not go overboard. So the first one is about interpretation, right? Ecological fallacy. The second one is about the scale of observation. And just as, you know, in any analysis, the scale of observation is actually something that may not be under your control. If it is, that's a different story, and then we can apply some of the clustering techniques that we talked about in the fall to get optimal units of observation, but oftentimes you don't control that. And there's a classic study in the 70s by Stan Openshaw, which was entitled "A Million Spatial Autocorrelation Coefficients." And basically what he did is he took electoral data from Iowa and computed Moran's I spatial autocorrelation coefficient. We'll talk about that in a few minutes. And he did it at the ward level, and then he went up to larger and larger units of aggregation. And what he observed is that, in fact, this autocorrelation coefficient not only changed in magnitude, but also changed in sign. So in other words, the results of the analysis are a function of the scale at which you do the analysis. And that's a problem. And that's not specific to space, but in spatial analysis, it's in your face, because you really have to deal with this. And not only it's not only a size issue, but it's also a spatial arrangement issue. Remember when I mentioned the differentiating characteristic is that location and arrangement matter. Well, these are things that come at you in this MAUP, this modifiable areal unit problem. And let me illustrate this with just an imaginary example. So let's say we start with 5 regions up on the top left. And so we can change the size. So instead of having 5 regions, we can cut them into smaller units and then do the analysis at the smaller unit scale. Or we can keep the 5, but arrange them differently. You know, gerrymandering, right? You take the individual units, electoral districts, and you put them together differently, and you get different results, right? And then ideally, unfortunately, we won't have too many examples of this. Ideally, you can work at the individual level, and then the whole aggregation thing goes away. And you can deal with location, distance, relative positioning at the individual level. So just something to think about as you look at your data sets. Is this scale of analysis, is that something that is meaningful for the question that you're asking? And you know, I always say work at the smallest possible level that you can, because you can always aggregate up. Going down is a different story, right? And then another version of this, it's a little bit a variant, if you wish, is the change of support problem. And the change of support problem is really a data problem. It's when your data are measured at different scales. And for example, if you're interested in the effect of, say, air quality on health, right? So you have health statistics by zip code or census tract or something like that. And then you have 30 air quality monitoring stations. Those are points. You know, the zip codes or census tracts are areas. So how do you combine these two, right? Or you're looking at educational policy, and you have school districts. But school districts don't line up with census tracts or any of these other things. So you have census data, you have school outcome data. How do you mix them together. That's the change of support problem. And so it's relatively straightforward when the spatial structures are hierarchical and nested. You know, so census blocks go into census tracts, and so you build up vertically. That's relatively straightforward. But when they're non-overlapping or non-nested, that is a much more complex problem. And so that is, in GIS world, that's the spatial overlay problem. You know, how do you create data situations that actually mesh? And so you can carry out your analysis. So the two main solutions are basically different forms of cop-outs, right? I mean, this is a problem that doesn't really have a solution. But one is aggregate up everything to a common level. So if your data are all at the county level, even though you have school districts and other things at a smaller level, you move them all up to the county level and do your analysis there. And of course, then you run into the ecological fallacy, potential problem, and so on. Another solution, which is much trickier and requires some pretty heavy-duty Bayesian analysis, is imputation. Imputation is basically making fake data. I'm exaggerating, but it's making data where data don't exist, right? So if you have, say, I mean, there are companies that do this, right? If you have ever worked with census tracts historically, you know, the census tract boundaries, they change over time. So if you do historical or time series analysis, how do you deal with these changing boundaries? Well, you have to somehow get them all to be on the same boundary. So how do you allocate populations to these new little pieces that you're creating? And you do that by running a model that has data at very micro scale, things like, you know, building permits or postal office data, you know, those school enrollment data, those kinds of things that are the very micro scale. You use those to build models to essentially interpolate. And in the Bayesian framework, this is borrowing strength. That is the bottom line Bayesian principle is when your information is not reliable enough, you borrow strength from information that's elsewhere. So then you build these really fancy imputation models that create data for aerial units that you don't actually observe. So that's just to give you something to think about before we get into the actual meat of things, the actual analysis. So, so the next two topics are a review of spatial autocorrelation and spatial autocorrelation statistics, and then the concept of spatial weights. And if you've never done any spatial analysis, I just have to warn you, this concept of spatial weights is weird. And some disciplines, and particularly economics, are very uncomfortable with it because it's too ad hoc. It's not based on theory, and it is ad hoc. But in a few minutes, you'll see why. There's really no other way around. It's a problem. It's a data problem. You know, you can't model interaction with a simple cross-section. That's the bottom line. So we'll get to that in a few minutes. First, spatial autocorrelation. It's good to think a second, what is the null hypothesis? So the null hypothesis is the point of departure, is kind of like a straw person. It's something that you set up, but you're actually not really interested in it because it is not interesting. Spatial randomness is the null hypothesis. Basically means anything can happen anywhere. There's no rhyme or reason. There is no pattern. There is no structure. Randomness is random. You cannot explain randomness. You can make a model, mathematical model, that tries to reflect the randomness, like a normal distribution or some other distribution, but it doesn't explain anything, right? So what you really want to do is reject a null hypothesis. Because if you reject a null hypothesis, then that means there is some structure. So there's a difference, a bifurcation between exploration and modeling. You know, if you're exploring, so you try to find patterns, clusters, hotspots, cold spots, you want to reject a null hypothesis because that means there are patterns, right? If you do in regression analysis, you actually don't want to reject the null hypothesis, because the null hypothesis is the sandcastle on which your whole modeling and estimation and testing is built. And if that doesn't hold, you have to go back to the drawing board. So if we reject the null hypothesis of spatial randomness in a spatial regression context, we're basically in trouble, because that means that some of the basic underlying assumptions of the regression analysis, and we'll get into that next week in some more detail, is not valid. So then what does that mean for our estimates? Are they biased? What does it mean for their standard errors? Are they off? What does it mean for our measures of fit? Are they misguided? You know, so there's a difference. In exploration, you want to reject the null, because then you find the patterns. In regression modeling, you really want to have all those patterns in your model. And what's left, the error term, should conform to the null hypothesis, because then you're fine. Everything is following the rules. Every interpretation is the way it should be, because at the end of the day, all this business is just quantifying uncertainty, right? Things are not certain. They're not deterministic. So they're give or take, but give or take how much? And how do we get a good value for what that how much is? That's what this is all about, right? So if our assumptions hold, then we know mathematically, formally, exactly what that precision is. But if they don't hold, then we have to figure out what kind of adjustments do we need to make. And that's what a lot of the topic of this course is about. How do we need to change our estimation methods? How do we need to change our measures of standard error and variance and so on? So that's the null hypothesis. So if we reject the null hypothesis, what do we get instead? And underlying all of this is what people call Tobler's first law of geography. Waldo Tobler was a colleague of mine in Santa Barbara, and he just came up with this. And it's basically kind of almost a tongue-in-cheek law. Everything depends on everything else, so society is complex. We knew that. But closer things, more so. And so, in some sense, this is circular reasoning, okay? Because you can say, okay, closer things are more similar. But then if you step back a second and say, well, how do I define close? If I define close as being more similar, then we're just turning around in a circle, right? And think about this for a second. I know those of you who do machine learning and those kinds of things, we're often interested in closeness in multi-attribute space. So if you think of a data point, say, let's just take 3D because we can visualize that. So you have a data point which measures on 3 variables, and another data point also measures on 3 variables. If they're close to each other in multi-attribute space, they're very similar, they're close, right? But the key thing here, the complexity that we introduce here, is we superimpose on this attribute closeness the concept of, let's just call it geographical closeness. It doesn't have to be geographical, it could be network closeness, but it's a different concept of closeness. And it's the combination of these two that is tricky. So Tobler's law seems like a circular reasoning, but it really, the point that it brings home is that there are 2 different things going on here. One is attribute similarity. The other one is geographical or network similarity. And getting these 2 together is what the challenge is that we face here. So the importance, and we'll see this later in a much more technical way, is some kind of notion of distance decay. And the notion of distance decay is such that you simply cannot have that everything depends on everything else equally strongly. That is a situation with no information whatsoever. And we'll see formally later on that is a situation where your coefficient is 1, and when it's 1, the system is singular. There's no solution, Right? So you can't have that. You have to have some way of decay of the correlatedness, of the connectedness. And typically we call this distance decay in a geographic sense, but it is distance in a general sense. So basically the bottom line is if you have spatial correlation, closer things are more similar than they would be randomly. That corresponds to a loss of information. So how do we correct for that loss of information? We correct for it by moving far enough away so that there is no more correlation, and then we have the information back. So think about this when we do the very fancy asymptotic stuff that we'll be doing later, because that's basically all it is about. It is a mathematical way of thinking about moving far enough away so that we get the information back as independent pieces of information. If you're too close, they're too correlated. So what you observe in one location already tells you a lot about what happens in the next location. So then that next location doesn't bring a lot to the table in terms of additional information. So if you move far enough away, there's no more connection, and then that next location brings independent information to the table. And that's what in statistics it's all about, is variability, it's information. You know, in the standard textbooks, all the observations are independent and identical. In space, they're not. Okay, and that's one of the main complications. So positive spatial autocorrelation is an impression of clustering of like values, and I stress the point, like values are closer by. So you tend to be surrounded by other observations that are similar, have similar values. Right? So I stress like because it doesn't mean anything about magnitude. And there is a classic, you know, there are some classic cases where positive spatial autocorrelation has been interpreted as the coincidence of high values. But in fact, it was the exact opposite. You know, if you look at it, the example is the stroke belt. There were some studies that, you know, a while ago that looked at the stroke belt and concluded that high positive autocorrelation meant that areas with high stroke incidence were located in similar geographical areas. In fact, it turns out that statistic was driven by areas with very low stroke incidence being in similar locations. So it's not about high or low, it's about similar, right? And may have seen this picture before. Forget your eyes. Your eyes fool you. Your brains fools you. The human brain is wired to see patterns. So you see patterns even when they're not there. And that's what this business is about, you know. So all too often I see people making presentations in front of a map and they say, I see a cluster here and there's a cluster there. Well, you see clusters everywhere. That doesn't mean that it's a real cluster. So the business that we're in is quantifying that. Again, quantifying, in a sense, the uncertainty. How real is this cluster? How do we know with some degree of certainty that this cluster is really a true cluster and not just some fluke that could have happened by accident, right? And so as you can see, you know, this is not that easy to differentiate. So what I did here is run a little simulation where I create a random spatial process, and then I build spatial dependence in and start cranking up the parameter. So with the high enough parameter, you start seeing the grouping stronger and stronger. With low parameter, you don't see it that well. So positive spatial autocorrelation is basically a loss of information because close things are more similar than they would be randomly, right? Negative spatial autocorrelation is the opposite. And conceptually, this is a little difficult to think about. So what is negative clustering? You know, there isn't really a clean concept of that. But think of a checkerboard. So whereas in some sense, positive spatial autocorrelation is a loss of variability. A loss of variability because you have these chunks of similar values. Negative spatial autocorrelation is more variability because you have high, low, high, low, high, low, high, low. Much more variability than you would have randomly. So it's a different thing. It's really, even though mathematically it's a negative sign of a coefficient, qualitatively it's a very different thing. So negative spatial autocorrelation you can almost think of as additional heterogeneity that somehow needs to be controlled for, whereas positive spatial autocorrelation is a loss of information because things are too similar in similar locations. So this is much trickier. If you ignore my annotations, try to honestly for yourself tell the difference between these two patterns. One is random by construction. The other one has a very high degree of negative spatial autocorrelation. So this is where the test statistics come in. This is where the modeling comes in to be able to quantify and to detect these patterns. And so the concept of a spatial autocorrelation statistic is really something that combines the notion of attribute similarity and locational similarity. And a statistic, you know, as you probably know, is just something that you construct from the data, right? So you could look at data on a map and say, well, what would be a good spatial autocorrelation statistic? And you might say, well, what about the maximum value? Well, we already know, since the maximum value doesn't tell us anything about where that happens, it won't be a good spatial autocorrelation statistic. So we need to come up with something that we can compute from the data that combines the notion of attribute similarity, like a correlation, with something that expresses formally the notion of locational similarity. You know, geographical neighbors or network neighbors, right? And that's the tricky part. So the attribute similarity is easy. The locational similarity is the hard part. That is where the spatial weights come in. So if we have attribute similarity, there are a number of different measures out there. You're probably very familiar with some of them, like a, you know, Pearson correlation coefficient. That's just a cross product, right? Dissimilarity would be square differences. You know, the square root of square differences is a distance measure. Absolute differences, these are all dissimilarity measures. So similarity measures have higher values when things are more similar. Dissimilarity measures have smaller values when things are more similar. So if they're very similar, the difference between them is very small. So they're kind of the opposite. So when you have a spatial autocorrelation coefficient that's based on a cross product, such as Moran's I, which we'll see in a few minutes, then high positive values are positive autocorrelation and negative values are negative autocorrelation. When you have a spatial autocorrelation statistic, say that's based on square differences, like Geary C, then it's the other way around. Then small or negative values are positive autocorrelation. I mean, just to, you know, you have to really think about that. And then positive values are negative spatial autocorrelation. So when the difference is large, high dissimilarity, the square difference will be a big number. When they're very similar, it will be a very small number. So it's the reverse of these cross-product statistics. As long as you know in which direction you're going, you should be fine, right? So the tricky part is, how do we combine this? So think of this in abstraction as a function that combines the value of a variable y at I with the value of a variable at a different location, y at j. So we need some function f of y at I and y at j. We can take the cross product, square difference, absolute difference, cosines. There's a whole bunch of these, right? The second thing is where we get into trouble, or start getting into trouble, is how do we define locational similarity? And if we have the luxury of having actual interaction data, then we can define the neighbors as pairs of observations, all the pairs of observations. But we often do not have that luxury. So we somehow have to formalize the weights, the neighbor structure for each observation/location. And we do that by means of this concept of a spatial weights matrix. And the spatial weights matrix is really an artifact. It's something that we need because we do not have enough information to model the actual interaction. We only have a cross-section, and we're really dealing with interaction. Spatial autocorrelation is about interaction. And we'll see later, you know, the theoretical motivations for these models come out of social interaction models and peer effect, copycatting, those kinds of things, right? So the spatial weights matrix, just think of it as a matrix W consisting of elements Wij, where Wij is 0 when I and j are not neighbors and takes on a non-zero value when they are. Question is, what should that non-zero value be? Should it be just 1, or should it be some function of distance between I and j, or should it be something else, right? That's where we get into trouble, so to speak. So as I mentioned before, typically this is set in the context of geographic space, but that is by no means necessary. You can really think of it as any space where there's a network structure. So if you have a network structure with nodes, and nodes are connected by edges, when there is an edge, there is a neighbor structure. When there is no edge, there is not. So you can do this for geographic space. You can do this for social networks. You can do this for industrial sectors, whether they trade with each other or not, and so on. So it's actually a perfectly general concept. The formalism, and I actually discovered this when I was doing my dissertation, which is just very recently, of course, that the formalism in formal mathematical social network modeling and in spatial autoregressive modeling, the equations are identical. Of course, the meaning of the equations is not the same, but the formal expressions is exactly the same. So W can be a geographical neighbor weights matrix, or it can be a social network weights matrix. It's the same thing, mathematically. So the general form of a spatial autocorrelation statistic is a combination of the attribute similarity and the locational similarity. And it's important that you think of it this way, because there are many different spatial autocorrelation statistics, but in essence, they're all the same. They're all double sums over all the possible pairs, at least conceptually. In a second, we'll see that, in fact, it's only a sum over very few pairs, right? A double sum of this attribute similarity measure, this function that combines the values of the variable. It's univariate, remember? Correlation is bivariate. Spatial autocorrelation is univariate. There's only one variable at different locations. So it's the same variable at two different locations. So we have this measure F for similarity or dissimilarity, and then we have these weights, Wij, for, say, locational similarity. Now the thing to remember, and we'll see it again in the practicum on Monday, is that this weights matrix is mostly 0. Okay? If you look at the weights matrix, spatial weights matrix for the counties in the US, there's a little over 3,000 counties in the US. So you can think of this as a 3,000 by 3,000 matrix. A lot of numbers, right? 9 million. But any county, on average, only has about 5 neighbors. So if you have a row in this matrix of 3,000 plus elements, only 5 of these are not 0. In fact, as a percentage, it's less than 1% of the 9 million that are actually non-zero. So most of this is actually very, very sparse. So the way you can think of this is that the statistic summarizes the similarity measures for the neighbors. I mean, mathematically, it's for all the pairs. But most of these pairs are zeroed out. They don't count. It's only the neighbors that count. So it's a a similarity measure for the neighbors. So in some sense, you a priori, and that's where you get into trouble, a priori constrain the interaction potential to some W matrix. And then you quantify that interaction according to that W matrix, right? So for a different W matrix, you may have a different interaction measure, right? And then the question is, where does this W matrix come from, right? And that is where you get into trouble if you don't have a good theoretical foundation. And in most cases, honestly, there isn't one.
So is that a function of product between two
No, this is actually perfectly general, right? So it's a comma, I mean, I'm sorry, it should be a comma, right? So it's perfectly general. It's any function. So it could be the cross product, or it could be the square difference, or it could be the cosine, or anything like that. Yes, you're right. There should be a comma there. Okay. So then just to make sure we're all on the same page, the Moran's-I statistic for spatial autocorrelation, who's familiar with this? Let me just, okay, so I'm not wasting my time totally. Okay, so Moran's-I is one of the most commonly used statistics for spatial autocorrelation. And is basically kind of a cross-product statistic. If you look at the numerator, it's the cross products. You can think of the cross products of the neighbors with the Wij, and then it's scaled by the variance, okay? Moran's-I is an incredible misspecification statistic, and we'll see that later. Why? Because it picks up just about any deviation from your null hypothesis. In a regression context, of course, you want it to pick up spatial autocorrelation, and it does that. But it also picks up heteroscedasticity, it picks up non-normality, it may pick up non-linearity. So it's great. If you do this test as a diagnostic and you cannot reject the null, you can say, I'm good, right? But if you reject the null, then you're nowhere. Because you know something's wrong, you don't know what is wrong. And so later we'll see alternatives that at least try to guide us a little more intelligently in a particular direction as to what should the model be. What are we actually misspecifying? So Moran's-I, everybody knows that. There will be a quiz. Just kidding. I don't have the time to grade them. So you have that going for you. So spatial weights. As I said, it's kind of, it's not ideal. It's something you almost have to do. And even the so-called solutions that get around the spatial weights always come back to the same problem. The problem is we are modeling interaction and we don't have interaction data. So think of, for example, North Carolina happens to have 100 counties. That means, you know, a matrix with 10,000 elements. It's symmetric, so half of that. So we have about 5,000 potentially parameters to estimate with 100 observations. You know, even with Bayesian statistics, you can't do that, right? So it doesn't work. And asymptotics doesn't help us because, in fact, it gets worse. As the data set grows in size, as n, which we call the size of the data, grows in size, the weights matrix grows with n squared. So as the data set gets larger, where typically with asymptotics you get in better and better shape, here you get in worse and worse shape because the n squared matrix gets bigger and bigger, more and more unknown parameters. So the only way we can deal with situations like that is, as I like to say, is to cheat. And you cheat by turning it into a simpler problem. So the complex problem is modeling all the interactions. We can't do that. But if we say a priori, you know, 99% of these interactions are not going to happen. And then on top of that, we say, well, the interaction for all the other ones is of the same scale, translated one parameter, then we're in business. So now we have simplified the problem of estimating some 5,000 potential parameters into estimating one. Now, that's a big step, right? And it's, you know, often criticized, and with good reason. It is a big step. But what else are you going to do? Right? You can't. I mean, one pseudo solution is, well, why not make it a function of distance? Okay. Which function of distance? Right? And which distance measure are you going to use? One of the practical issues is, you know, it gets back to geometry and geography. Are you going to measure your distance in centimeters or in kilometers? You know, the distance between the two same units in centimeters is going to be a much larger number than in kilometers. And if you use inverse distance and you don't pay attention, you end up with a whole bunch of zeros. Because you divide 1 over a distance in centimeters, which is going to be millions of centimeters, and so you have 0. So, you know, even though from a particular perspective, using functions of distance may be theoretically more acceptable, and I can actually buy into that to some extent, you don't get away from the problem that you have to specify your distance decay function, and then you have to estimate the parameter, and it still is only one parameter for all the interaction. To some extent, if you have time series data, you can get around this problem. And in fact, there's some really recent literature on estimating the interaction structure from the data. But there's a caveat here. So you use the time series dimension to get the cross-sectional dependence, but that, of course, assumes that this cross-sectional dependence is constant over time. So even though that seems to be theoretically more acceptable, and it is at some level, you still have to make assumptions. And so this is kind of something that I like to mention many, many times. It's okay to make assumptions as long as you know what that implies for what you can say at the end of the day. You know, if you assume that everybody's the same everywhere and behaves in the same way, there isn't really too much you can say at the end of the day, right? So it's all a matter of degree. So, okay, where does the spatial weights matrix come from? Well, we take geographic neighbors. Is that appropriate? Maybe, maybe not. You know, if you know, you're looking at states and where they set their Medicaid rates, do they look at their neighbors? Probably. Maybe they look at neighbors in some other network space. So they look at neighbors in the political space. So the Republican-controlled states go one way, and they're all pretty much doing the same thing, and the other states go the other way, and they're all doing pretty much the same thing. There's strong spatial autocorrelation, but it's only geographic to the extent that the, you know, location of these states politically also matches their geographical location, which may or may not be the case. The essence is that we have a network structure, and that network structure gives us a handle to simplify the interaction process. And it is a simplification, because we are exposing this matrix structure. And, you know, we could have 2 of them or 3 of them, but it's just kind of, you know, Band-Aid, right? That it doesn't conceptually change what you're doing. Whether you have 1 matrix or 2 weights matrices, it's still only 2 parameters, and you should have a whole bunch more. So this is very important that you keep this in mind. So this is a shortcut, is by necessity, because we do not have interaction data. If you do have interaction data, you don't need these weights. You know, you model the interaction explicitly. So as I mentioned, the solution is structure. We limit the number of parameters that are estimated. As I mentioned, you know, asymptotics don't help us. We have what we call an incidental parameter problem, which is where the number of parameters grows with the sample size, so you don't gain anything. So we get these weights. And the weights constrain the number of neighbors, say only those that share a border, which is a very easy criterion. There's only 1 parameter, the spatial autocorrelation coefficient or the spatial autoregressive parameter. And then very importantly, and this is often kind of shoved under the rug or sometimes even forgotten, is that you are at the end modeling interaction. Even though you only have cross-sectional data, you're modeling the interaction. And the interaction consists of two parts. One part is the weights. The other part is the parameter. So to put it very crudely, if you have big numbers in your weights, your parameter will be small. If you have small numbers in your weights, your parameter will be larger. So the interpretation of the magnitude of the parameter is meaningless without knowing what this weights matrix is. And that's why we often standardize the weights matrix in some ways, so that at least we know the parameters are going to be less than 1 in absolute value, so we can somehow compare them. But if you don't do that, and for example, a lot of the Bayesian analysis does not standardize the weights matrices, and there's good reason for that. So then these parameters can have very strange values, and you can end up with a model, for example, where 0.00053 is a highly significant positive autocorrelation coefficient. Whereas in the linear models that we will be dealing with initially, that would be, insignificant. You would want to have 0.5 or 0.6 as a magnitude. So the magnitudes of these coefficients by themselves don't mean anything if you don't know what's in the weights. It's the two together that give you a sense of what the interaction is about. Okay, a little bit of geometry. These are my 6 sample regions. How do we get to the weights matrix? Well, we can think of it, as I mentioned, as a network structure. And we can think of each of these regions as being a node in a network and their common boundaries as edges connecting those nodes. Right? So then we have our network structure with the nodes and then the connections. And then, as you probably all know, one way to mathematically describe the structure of a network is in a matrix. A matrix with as many rows and columns as you have nodes. And then if there's an edge between nodes I and j, there's a number in the matrix. If there's none, it's a 0, right? And that's essentially what your weights matrix is. It is a description of the network structure. And typically that network structure, or I should say typically, in most of our applications, the network structure will come from the geography, but it doesn't have to. It can come from a social network structure. So formally then, the spatial weights matrix is a n by n. N is the size of the data set. Positive weights matrix. It's positive by convenience. If you go negative, things can get very messy. Wij is the weight between I and j, 2 different locations or observations. By convention, the diagonal is 0. So no self-neighbors. That is not an absolute requirement. You can have situations where you have self-neighbors, but the math gets much more complicated. And we'll see that technically, you may be familiar with the notion of a trace of a matrix. The trace is the sum of the elements of the diagonal of a matrix. And if the trace is 0, that's easy, because that means the trace doesn't change with the size of the data set. So if you have a bunch of zeros on the diagonal, that trace will always be 0. If you have a bunch of 1s on the diagonal, self-neighbors, then that trace will increase with the size of the data set. And that's not a good thing. We'll see later more formally when you do asymptotics and those kinds of things. You want things to go to 0 as n goes to infinity. You don't want things to go to infinity when n goes to infinity, which would be the case with the trace when you have 1s. So that's just a technical thing. So then let's just look at some examples. Geography-based weights, contiguity, common border is the simplest one. Share a border, you have 1. You don't share a border, you have 0. That's pretty straightforward. So this is the weights matrix on the left, the actual matrix that corresponds to the network structure that we have with the common neighbors in our little example. One slight complication is that the notion of neighbor in geography is not without ambiguity. Even on a regular grid, we can look at neighbors that have a common edge. We call that rook neighbors. We can look at neighbors that have a common corner. We use those bishop neighbors. This is chess terminology. And then we can combine the two. We call them queen. Now, why is this relevant? Well, if you have rook neighbors on a grid, there's only 4. If you have queen neighbors, there are 8. So there's much more information incorporated in a queen neighbor structure, everything else being the same, than in a rook structure. And so even in irregular data sets, there is a difference. But I had to look very hard to find these cases. These are kind of artifacts to some extent, where you have corners situation. So when you have corner situations, then there will be a difference between the notion of rook weights and the notion of queen weights. And you can check this out if you have a map of the US. Solano County in California, there's a difference between rook and queen weights. And you see at the bottom map, this unit that kind of has a wedge and touches at the very corner is included as a neighbor. The top part, we only look at the common actual borders. It is not. And these cases are not that common, but they do occur, and it can matter. You know, it's not an absolute thing. So distance-based weight, and we'll go over all this in much more detail on Monday with some illustrations. Distance typically between points or between point counterparts for areas. So an area can have a central point, and so then you compute the distances between the central points. And so any function of distance you can use, typically it's a distance band. You have some kind of critical distance where you say if we're beyond that, it's 0. Within that, it's a 1. So this is critical distance. We'll see on Monday there tends to be, when you have highly irregular units, there tend to be problems with isolates or islands or unconnected units, and then we have to make decisions about that. K nearest neighbors is just forget about distance. You take the nearest ones. The problem there in practice is what you do with ties. So 2 units are equal distance apart. Which one is a neighbor and which is not? Because you say K equals 4, for example, only 4 neighbors. Now, you know, the 3rd, the 4th, the 5th, and the 6th one are all the same distance. What do? I take all 6, or I only take 4 and kind of randomly pick 2 from the 4 that are equal distance. And so these are kind of things you have to think about in practice, not in theory. So then transformations, just one I will talk about is row standardization. So you rescale the weights so that each row, so the weights for each observation with respect to all of its neighbors sum to 1. Later we'll see that this helps us a lot in defining a concept of a spatially lagged variable, which turns out then to be a simple average of the neighboring values. It also helps us, as we'll see later, in constraining the parameter space. Remember I said parameter times the weights. If you row standardize the weights, you control the magnitude of the parameters, so that makes things more comparable. So this is an example of that. Higher order weights, it's neighbors of neighbors. It's a recursive definition. So what is a second order neighbor? A second order neighbor is a first order neighbor of a first order neighbor. But we cannot have circular paths. So if you look at this network structure here and you see the connection, so to get from 4 to 3, how do we get from 4 to 3? We can go via 2 and then 2 to 5 to 3, or we can go directly to 5 and then to 3. So one is 3 steps, the other one is 2 steps. So we only want to keep the shortest path in this. And so operationally, it's a little tricky to eliminate circular paths and redundant paths, and that's what one of the readings is about, how you do that efficiently. But basically, for all practical purposes, you just remember the recursiveness. So you construct, and we'll do this on Monday, first order neighbors, right? Then what are the first order neighbors to those first order neighbors that are not already first-order neighbors. Those are the second-order neighbors. So this, you don't have this in time series, right? Yesterday, the day before yesterday is not today. In space, it is, so to speak. So you have to think about this a little bit differently. Just think about this. So we can define contiguity either in a strict sense, which we'll do when we do our spatial econometric models, or we can do it in a cumulative sense where you can think of it as a counterpart to a growing distance band. And we'll do all that stuff on Monday in the practicum. Then finally, the properties of weights. So we can summarize the properties of the weights in a histogram or in a map. Basically, what we're looking for is the distribution of the number of weights. So how many observations have the number of neighbors, sorry, the neighbor cardinality. How many observations have one neighbor? How many observations have two neighbors? And so on. So what we want to get, and we'll see some examples on Monday, is a nice unimodal symmetric distribution. What we don't want to get is a bimodal distribution, where some locations have very few neighbors and some have very many neighbors. If we see that, then we might think about introducing structural change, spatial heterogeneity. What we also don't want to see, and I just want to spend a couple of minutes on this, is isolates. What do we do with observations that don't have any neighbors? Right. So when they don't have any neighbors, they're not in the network. You know, you still have them as observations, but they're not connected to anything. So if you're interested in modeling interaction, they're not playing, so to speak. They're not interacting with anything. They're not part of that game. So for all practical purposes, those observations are removed from any model for spatial interaction or any test for spatial autocorrelation and so on. Does that mean you have to remove them from the analysis? Well, not necessarily, because they're still there. They're only not interacting. So as far as the spatial interaction goes, they're irrelevant. But as far as relating, you know, in a regression context, covariates to the dependent variable, they are still playing because that is a non-spatial interaction phenomenon. So there's a choice here. If you're purely interested in the spatial interaction, then you either remove the isolates or you make them non-isolates. For example, in the US, there are some counties in North Carolina. I don't know why I keep using North Carolina, but it just happens to be that way, that are islands. And so they're not connected to the mainland. So how do you make them, maybe it's not in North Carolina, but just think of it as some county is an island and the rest of the state is the mainland. That county, for all practical purposes, will be eliminated from the spatial analysis. So that's one thing you can do. You know, I just did an analysis, a historical analysis for département in France, and there's 86, but I took out Corsica because it's an island, so there's 85. I do the analysis with 85. Or I could say, well, Corsica is really connected to its nearest neighbor on the mainland, and then we're back in business. Then we have a fully connected weights matrix. We have 86 observations. We're back in the game. Now, when you do that, you better have a very good reason. Don't do it ad hoc, right? And so, for example, you know, another example is in Detroit. When you look at census tracts, you know, the Detroit River, and then there's the whole Renaissance thing where GM used to be. That is technically an island, right? So obviously it's not isolated from the rest of the city by no means. So how do you connect that with the rest of the city? You look at where the bridge is. And so there you make a connection. So there's these kinds of issues to deal with. So we really want to think about isolates. So what we want to watch for is isolate situations where you have very large number of neighbors, and that is a bad thing because, as we'll see later, it's essentially a smoothing process. So if you, smoothing means losing variance. In statistics, everything is about variance. Everything is about variability. If things don't vary, there's nothing you can say, you know. If you, you know, regress things on constants, you're not going to learn very much, right? So you want things to vary. If you smooth too much, there's not enough variability, and so you lose too much information. So you want to know about that. You also want to know about bimodal distributions. And my classic example here is not North Carolina, but Virginia. Virginia has counties that are city counties and then regular counties. So if you look at the connectivity histogram for Virginia counties based on simple contiguity, you have a spike at 1, and then you have another kind of regular symmetric distribution. And the spike is 1 is all the city counties. They have one neighbor. It's the county that's around them. They have no other neighbors. And then all the other counties have kind of, you know, a normal, if you wish, neighbor structure with 4 or 5, you know, neighbors as they usually. So how do you deal with that? Well, again, it's a smoothing thing. So if you only have one neighbor, there's no smoothing going on. Your spatially lagged variable is the value for your neighbors. That's it. And so whether you want to keep that together with these other ones, where there is a smoothing going on, that becomes sometimes a theoretical question, sometimes an empirical question. My point here is you should be aware of it. So what we're going to do on Monday is go through this in GeoDa space, and a little bit in R if we have time. So that will be kind of like a lab, but without being a lab. It will be mostly me running it here, and then if you have any questions. So I apologize. I just kind of went full blast, but you know, it's a review, right? It's supposed to be a review. So it's everybody's on the same page now, so we can move on. Monday will be about making sure that you can use the software for those of you who are not familiar with it. Again, for others, it will be a refresher. I will show you the latest version of GeoDa, which nobody has seen because it's not available. It's just on my laptop. And so I can show you some new things that we have in there, but